In this video, I'll be discussing about the magnetic force on a moving charge. So, in the previous classes, you have studied that the presence of electric field is due to the presence of a charge. So, if there is a charge, there will be electric field around that charge. Depends upon what kind of charge. If it is a positive type charge, you have a electric field coming away from the charge. If it is a negative charge, electric field will be coming towards the charge. So here, what about the magnetic field? You might have experienced when taking a bar magnet. If you bring a coin or if you bring another magnet just near that magnet, you may feel a repulsion when a magnet is bought or attraction when a magnet is bought. But always you see attraction when you bring magnetic materials when just towards that magnet. So this means that every magnet has magnetic field around it. So every magnet has magnetic field around. Unlike electric charges, magnetic field doesn't have a starting point. These are just closed curves. Okay, and the direction of magnetic, if you take the magnetic field, if you take it, starts from the north pole and it feels like it is ending towards the south pole. It always starts from the north pole and end towards the south pole. Now I told you in the previous video that magnetic field is represented by the symbol B. Magnetic field is a vector quantity similar to the properties of electric field lines. Magnetic field lines also obeys the law of superposition principle. Suppose you take a lot of magnetic field. So magnetic field B1, magnetic field B2, magnetic field B3, and many magnetic fields are there in a given space. Then the net magnetic field, okay, let me consider there are many magnetic field in a given space. Then the net magnetic field is equal to the sum of each magnetic fields. So B1 plus B2 plus B3 and so on. So magnetic field is a vector quantity. It has both magnitude as well as direction, and it also obeys the superposition principle law. Now magnetic field can be represented by dot marks or cross marks. So if magnetic field is represented by a dot mark, it means to say that the magnetic field is coming outside this plane. So on this board I have mentioned a dot here. So on this board I have mentioned a dot. This dot represents that magnetic field is coming outside the board. So here I have mentioned a cross mark or into mark. So if it is into, it is going into the plane. So this is how these two are the symbols what we use to represent magnetic field. If it is just a dot mark, it says that magnetic field is coming outside the plane, and if it is a cross mark or into mark, it is going into the plane. So now let me come to the main topic. So magnetic force on a moving charge. So if there is a charge just at rest, so that is electrostatics. So if a charge is in motion, moving charge constitutes electric current. So in the Orchid's experiment, I just told you that moving charges also associates with magnetism. Moving charges constitutes electric current. If there is a moving charges, it constitutes both electric field as well as magnetic field. Okay, it is proved by Oersted. So here let me consider a charge is moving only in magnetic field. So let Q be a charge. This charge you consider it is moving perpendicular. So let this Q be a charge. Let this charge moves in a magnetic field. So here is a magnetic field. So I am representing the magnetic field by dotted symbols. So dotted symbols represent that magnetic field is coming outside the plane. So I consider a charge Q is moving with a velocity v in this direction. So this is the direction of velocity of the velocity of the charge, and magnetic field is coming in this direction. So now so a force will experience on the charge. So what is the direction of force experience on the charge? Is force experience in perpendicular to that of the velocity of the charge as well as perpendicular to the magnetic field. So here we give the expression by force is equal to Q into V cross B. So force is equal to Q into V cross B. This means that a force depends upon velocity as well as magnetic field. So point wise I discuss. First one, Okay, so it is, so so this is just not told as into, this is q into v cross b, so it is a vector product of velocity as well as magnetic field. The force depends upon the vector product of velocity and magnetic field. So force is zero either when the velocity of the charge is zero or the magnetic field is zero. So this means that a charge experiences force when the charge moves in a magnetic field. So, okay, when the charge moves, if the charge is at rest, the velocity is zero, then there will be no force. If the charge is not moving in the magnetic field, then the magnetic field is zero, then there is no force. Okay, now force is minimum and force is maximum. In which all the condition force is minimum? You know by vectors, A dot B is equal to AB cos theta. So this is dot product, and A cross B is equal to AB sin theta. So here V cross B I can write as, okay, V cross B can be written as F is equal to Q into VB sin theta. So sin 90 is equal to 1. When sin theta is equal to when theta is equal to 90, sin 90 will be equal to 1. So force will be maximum when theta is equal to 90 degree. Force will be maximum when the angle between the velocity of the charge and magnetic field is perpendicular. When they both are perpendicular, the force is maximum. When the charge moves perpendicular to that of magnetic field, force is maximum, and when the charge moves parallel to the magnetic field, the force is zero. You see, the magnetic field, I told it is coming outside the plane. So magnetic field is coming outside the plane. When the charge is also moving outside the plane, then the force is equal to zero. So this is the concept of charge moving only in a magnetic field. Thank you.